everybody. Today we're going to be talking very briefly about percent yield. Now we're still working on our unit on stoichiometry, and so part of what we're doing today does obviously involve stoichiometry. But today we're going to be looking at percent yield, which if you will imagine actually doing an experiment in the lab and trying to produce a certain amount of product, this is how we determine how successful our experiment was. Did we produce in the lab as much product as stoichiometry or math, our calculations, say that we should? Okay, so when we're looking at percent yield, what we're actually calculating is the percent of product produced in a lab experiment. So compared to what math stoichiometry says we should have gotten, how much product, how many grams of product, what mass do we actually produce? And then we'll calculate the percent from that. Now, here's our formula that we're going to use to calculate the percent yield. This is not percent error, so there's no subtraction here. This is percent yield. And our formula is the experimental yield, and sometimes we refer to that as the actual yield, so what we actually got in a lab experiment. The experimental or actual yield divided by the theoretical yield. So the experimental yield comes from lab data, right, what we actually got in lab. The theoretical yield is what we're expected to get based on stoichiometry, okay? So when we do the math, we know how much reactant we're starting with or how much of each reactant we're starting with. When we do the math, we can figure out how much product we should form. That's the theoretical yield. How much product should we form compared to what did we actually form, okay? Now, I'm just going to go over one brief example. I'm actually going to go this way. Which is going to be similar to the lab that we see for this unit. Okay, so our example, we have nitrogen gas plus 3 moles of hydrogen gas, giving us 2 moles of NH3. Okay, so in a lab experiment, 4 grams of hydrogen gas is reacted with 36 grams of nitrogen gas. Hydrogen is a limiting reactant. Now, I've told you which one's a limiting reagent, so you do not need to figure it out. From this point forward, every calculation you do is going to involve that limiting reagent. So hydrogen, the 4 grams of hydrogen is what we're going to use in our first calculation, okay? If 17.5 grams of NH3, that's the product, if 17.5 grams is actually produced in this experiment, what is the percent yield of NH3, okay? Now, I put this in green. 17.5 grams is the actual amount that we produce in the lab. We're going to need to calculate, in order to do the percent yield, we need to calculate how much should theoretically be produced. Okay, so we produce 17.5 grams. Stoichiometrically, how much should we produce? Okay, so that's what I set up down here. Notice that I'm starting with 4 grams of hydrogen because why? Hydrogen is a limiting reagent. Okay. Once we know that, we start with the limiting reagent. I have 4 grams of hydrogen on top. I need to get this into moles of hydrogen. So I have the molar mass of H2, 1 mole of H2, and my grams of H2 cancel out. Okay. Then we go here. What is this step called? This is our mole-to-mole ratio. Okay, so I'm going to look, where am I looking for this? I'm looking at my balanced equation. I have moles of H2 on bottom, and if I look up here, I see that there are 3 moles of H2 in that balanced equation. And on top, I'm trying to get to the substance NH3, so it needs to be moles of NH3 on top. If I look at my balanced equation, I have 2 moles of NH3, okay? Moles of H2 cross off. Now we're in moles of NH3, but we need to know what mass, because this is given to us in mass, in grams. We need to know what mass of NH3 should be produced, theoretically. So, for every 1 mole of NH3, the molar mass is 17.04 grams. Moles is gone. And we find out, stoichiometrically, that we should, with 4 grams of hydrogen and excess nitrogen gas, we should be able to produce 22.5 grams of NH3. Okay? Now we can plug that into our percent yield equation. Actual over theoretical. Okay? So we just need to look here and see which one is actual. Well, I have it in green. Actual, what we actually produce in the lab, is 17.5 grams of NH3. What is our theoretical yield? This is stoichiometrically what we should have produced, given our reactants, 4 grams of hydrogen and 36 grams of nitrogen. We should have produced 22.5 grams of NH3. Okay? I'm including sig figs here, right? 3 sig figs because I started with only 3 sig figs. Okay? Now, 17.5 divided by 22.5, and we have to multiply by 100 because we're trying to get this into a percent. And when we multiply by 100, we get a broken pen cap, 77.77. Now remember, we need sig figs. We have 3 sig figs in both of these. So this is 77.8%. Okay? What that means is that in our experiment in the lab, we produced 77.8% of what we should have produced. Not an incredibly successful experiment. Our goal is always to be producing 100% of what we should be producing. If there are no errors, right, not just human error, but some unavoidable lab errors, if there are no errors, this is 100%. So the better percent yield, the higher the percent yield, the better your experiment protocol was. All right, so we're going to see this in our lab if we haven't already, and we'll be calculating the percent yield of magnesium oxide.